All right, we're going to do the solutions for the one trophy level we did not do in class. So we did the apprentice and master levels on the angle watched projectile mathematics activity on physics classroom. We will now do the wizard level. So in this case, we don't have any two rows with the same information. So each will be its own separate problem. Our first one, we are given the initial velocity and the initial angle. We have to find the time it takes it to move up, the total time in the air, the horizontal distance, and the height at its peak. So we will scroll past the problems we had for the 1D kinematics and work with our initial velocity, or the V0 as they call it. The original velocity is 38.8 meters per second. And our angle theta, which is usually a lowercase, and they've got the capital, but that's 56.2 degrees. So the time up, to figure that out, we need to take a look at what we know. If we look only in the y component, because that's going to determine how far it goes vertically, we're looking for our distance, our initial velocity, our final velocity, our acceleration, and our time. If we are looking to the peak, our final velocity is 0 meters per second. Our initial velocity will be 38.8 meters per second times the sine of 56.2 degrees, because our initial vector is up at that 56-degree angle. So the horizontal component and the vertical components come in here, where this angle is the angle that we measure. It's relative to the horizontal. That makes the vertical component the opposite side, so that has the sine function when we know the hypotenuse, and the horizontal will use the cosine. So 38.8 times the sine of 56.2. Our initial velocity in the y direction, I'm going to slide over a little bit here so it fits, is 32.2 meters per second. Our acceleration we know is a negative 9.81 meters per second squared. So now we can figure out the time and the distance. So the distance we can get with Vf squared equals Vi squared plus 2AD, where our Vf is 0. So that means our d is a negative Vi squared over 2a. So we take that last answer we had and square it, divided by 2 times a negative 9.81. So that negative and the 9.81 for the acceleration cancels this negative here. And our distance is 52.98467348 meters per second, or 53.0 meters. Sorry, just meters, not meters per second. My apologies. So there is our distance, there is our velocity, and for our time, you can say that A is Vf minus Vi over t. So then our time is Vf minus Vi over A, which is a negative 32.2 meters per second. Careful to use all the digits we had in our calculator for this, divided by a negative 9.81 meters per second squared. So the time works out to 3.29 seconds. This is just the time up, but that's enough to fill in this blank in the table. And if I remember that this doesn't accept typing, I have to put it in that way. That would go much nicer, much more quickly. We also have our 53.0 for the peak. Our total time is going to be that time we just got times 2. So that is a 6.57 when we use all the digits in our calculator. So all we have left to solve for is the horizontal distance. Well, that horizontal distance, our dx, is going to be our x velocity times the time. Our x velocity is our 38.8 meters per second times the cosine of 56.2 degrees. And our time here, we use that 6.57 unrounded value from our calculator. So we put all of that together, and we get a number that rounds to 142 meters. So 142, we hit enter. We'll check our answers. And there we go. Our first problem is solved. And remember, in these chart questions, each row of the chart is like a separate problem. So it appears as one table, but it's really 5 questions to answer. Now we have our time up and our horizontal distance this time. The total time is much easier to get when we have the time up. It's just double what we had. So that one is just times 2. With our horizontal distance and our time, we could find our horizontal velocity. So our Vx, sorry, that one was my bad, put my hand on the pad. So our Vx is dx over the t total. In this case, that is 63.6 meters. I have to put brackets around all my substitutions. Divided by 4.70 seconds, which gives us 13.5319149 meters per second. Now, Vx is not one of the pieces of information in the table. It will be a component that we need for the initial velocity and the angle, but it's not here on its own. The next piece we need is to use that time of flight to figure out either the Vy or the distance to the peak. I'm going to use the equation d is Vft minus 1/2 at squared to figure out that height. Because if we're just going from ground level to the peak, our initial or the final velocity is going to be 0. When it's at the highest point, the vertical component of velocity is 0. So d is a negative 1/2 times an a of 9.8 or negative 9.81 meters per second squared. And our time to get halfway there is 2.35 seconds, which we need to square. So we have negative 1/2 times negative 9.81 times 2.35 squared. And we have a 27.0878625 meters, or 27.1. Right. So far, so good. Now that we have our height and our time with our acceleration, we can now solve for our velocity. All we need now is our VIY. We can get that by saying A is VF minus VI over T. And if we're looking again strictly at the vertical component, that is 0. Oh, sorry, we have to do some manipulation first. So yes, A is VF minus VI over T, which means VF minus VI is AT. So VI is VF minus AT which is 0 meters per second, minus a negative 9.81 meters per second squared, times the 2.35 seconds we had here. So our initial velocity in the y direction is 23.0535 meters per second, which rounds to 23.1. We will now use our unrounded values to figure out our overall velocity. So Vix was 13.5 meters per second. Viy, just for reference, was 23.1 meters per second. So our V naught, as they put it here, is the square root of Vix squared plus Viy squared. We always use the unrounded values from our calculator, so 53191. And 23.0535 meters per second squared. We take the square root of that. So we have the square root, just running all that through the calculator. It's 26.7315659 meters per second, or 26.7 meters per second. So we could fill that in here, 26.7. And now for our theta, we have to use the inverse tan. So theta is the inverse tan of the y component divided by the x component so that is the inverse tan of the 23.05 divided by the 13.5 works out to 59.6 degrees. All right, that solves problem 2. So problem 3, we are given the horizontal displacement and the DIY peak. That's it. So we're going to have to go to the time first, because that's the piece that connects our x and y components. It's the time. So knowing the dy peak, knowing that happens when the y velocity is 0 and it happens with acceleration of negative 9.81 meters per second, we'll be able to figure out the time it takes to go up, and that'll give us the total time. And then with all of that information, we can figure out both of our initial velocities and work out the rest. So let's start by finding the t up. That we're going to use our d equals vft minus 1/2 at squared again. We know our vf is 0. This time we're given the d. We are solving for t. So we have a negative 2d over a. And we'll take the square root of that to find our time. And this will be specifically the time up. So negative 2. Our displacement is 27.1. Oh, wait, wrong row. 16.9. And our acceleration is a negative 9.81 meters per second squared. This negative cancels the other negative. So this gives us a time to go up of 1.86 seconds. So our total time, which is 2 times the time up, is 3.71 seconds. So there we go. We have 1.86 and 3.71. So that figures out our time. All we have left now is to figure out our initial velocities. So the Vx is a lot more straightforward than the Vy. That is going to be 70.8 meters divided by 3.71 using all the digits seconds. Or 19.07126126 meters per second, roughly 19.1. Our VIY. To get that, we use A is VF minus VI over T. So doing the same rearrangement we did before, our VIY is going to be VFY minus AT. So VIY is 0 meters per second because we're going to the top, minus a negative 9.81 meters per second squared. And our time, here we're just using the half time of 1.86 using the full 1.85619.606 that we see in our calculator. So our VIY will work out to 18.209283335 meters per second. So now our original velocity, square root of Vix squared plus VIY squared. So Vix squared was that 19.07126 that we use in our calculator, the complete unrounded value. And the y was that 18.209283335. Again, use that complete unrounded value in the calculator. And punching that in, we get a 26.4 when we round it, 26.368373132. So that is a 26.4. And our initial angle, so our theta, is the inverse tan of the y over the x, again using the complete unrounded values. So that gives us a 43.7 degree angle. So 43.7, and there we go. So now our third row is confirmed. For our fourth row, we're just going to have to go back and really figure out how things are working here. So in our fourth row, let's take a look at the information we're given. We've got horizontal, we've got vertical. So as I'm doing these charts, I'm going to think that the horizontal is the total, and the vertical is, I'm just going to treat it as the time up. Acceleration and the time. So let's take a look at what we were given. Why am I doing these scratchy lines when this has a built-in line tool? Should have used the built-in box tool as well. But anyway, let's take a look at what we know. We know our V0, and we know our DIY. So the distance here is the 28.2 meters. We know our final velocity is 0 meters per second. We know our acceleration is negative 9.81 meters per second squared. We have three pieces of information. That means we could find the other two. So we could find VI using the equation that does not involve time. So here our VI, in the y direction at least, is the square root of VF squared minus 2AD. So that's the square root of 0 meters per second squared minus 2 times a negative 9.81 meters per second squared, and times our 28.2 meters. Sorry, that's getting kind of scrunchy. Anyway, 2 times 28.2 times 9.81, and we want to take the square root of the answer. That gives us an initial velocity in the y direction of 23.5 meters per second with some extra digits. And our time we can now get so the time we can get ideally without that initial velocity, just because that there is that risk that if we messed up doing the initial velocity, if we use that also for time, we'll get both wrong. But if we could solve for time using only the information that was provided, recognizing again that our VF is going to be 0, then using that same manipulation we had before, our time is negative 2d over a, or the square root of that, sorry. So that's the square root of 2 times 28.2 divided by 9.81. Our time is roughly 2.40 seconds. It's actually 2.397756342 in the calculator. But again, we don't have that much information. So this will give us our total time. We can double it. That rounds to 4.80 seconds. Our acceleration is 0 meters per second. We only have one velocity here. So these will be the same. So now how can we figure that out? Well, we are given our total velocity, and we have calculated our y velocity. So that means the angle between them is given by sine theta is VIY over V naught. So our angle is the inverse sine of 23.5 meters per second divided by our initial overall velocity of 46.2 meters per second. So our angle is going to be very close to 30 degrees, I believe, if I'm doing my estimation correctly. 30.6061615 degrees. So that is now a big piece. That means our Vx, which is V naught cos theta, is 46.2 meters per second times the cosine of our 30.6061615 degrees. So that is 39.763752234 meters per second, or 39.8 when we round it. So now I think we just have the horizontal distance left to calculate, because we have, yes, 39.8 meters per second and 39.8 meters per second. And it travels that for about 4.8 seconds. We multiply velocity by time. And our horizontal distance is 191 meters. Now we've got what we need to finish that chart. Our angle, we said, was 30.6. Our time up, 2.40. Total time, 4.80. And our horizontal distance is 191 meters. All right, so we just have one left. We're given the angle, and we're given the horizontal displacement. Doesn't seem like a whole lot. Let's chart it out, and we'll see what actual information we have. Again, I am going to consider the horizontal the total time, and the vertical the time up. So there's 2 variables, 3 variables, and there's our 5 variables. So our x is total, and our y is just up. D, vi, vf, a, and t. We know our dx is 18.6 meters. Okay, and we know our angle is 22 degrees, and that is everything we know. So this is going to get a little bit complicated. We know we have 0 meters per second squared here, negative 9.81 meters per second squared here. On the way up, we have 0 meters per second. We don't have either initial velocity, we don't have that time. What we do know is that we can connect these, right? Because that time will link both. So this one is going to be a challenge mostly because it's a technique that's different from what we're used to. In order to completely solve for a variable in one of these equations, we need to have 3 pieces of information. We only ever have 2. That means we have to do this as a system of equations. We have to do this with parameters. So in other words, we know our x velocity is going to be the distance over the time. We know that our x velocity is our initial velocity times the cosine of the angle, and that angle is known, times d over t. So it means our time is the known distance over v naught cos theta. Now, I actually haven't done a problem with just this setup, so I'm kind of spitballing here. We'll see how well it pans out for us. The next piece is to say, we know that when this goes up, right, it hits that VF 0, we can figure out the time there. So the time up, I should mention this is time total. So the time up is going to be, I'm going to label that x, because we're going to have both floating around here. But the dx is known, remember. So here we do not know the initial velocity, but we know our time. Our time up we can do by saying, well, yeah, for example, let's say A is VF minus VI over time up, or just a negative VI over the time up, because the VF is 0. Now I think we're getting somewhere. That's a V naught sine theta. That time up is the total time over 2. So down here we have a dx over 2 V naught cos theta. Right. So rearranging that, we have A is negative 2 V naught squared sine theta cos theta over dx. It looks intimidating because it's more involved than what we are used to. But that means our V naught squared is A times dx over negative 2 sine theta cos theta. But our V naught is now known because we have all of this information here. So setting it up as a system with a parameter is a little more complicated than we normally do, but we can do it. We have a negative 9.81 meters per second squared. Our horizontal distance was on the chart, but it's also here, 18.6. Divided by 2 times the sine of 22 and the cosine of 22.0. So we have 9.81 times 18.6 divided by, and then in brackets, 2 times sine 22 times cos 22. Our initial velocity is 16.2 meters per second. So this is 16.2. We check it, it checks out. Now we can go back and start substituting into what we had. So with this now, our total time is our 18.6 divided by that 16.2 times the cos of 22. So that gives us a total time of 1.24 seconds. Oh, total time goes on the other side. Total time is 1.24 seconds, and the time up is 0.62 seconds. So here 0.62, and here 1.24. The last thing we need is that vertical time of flight. But now we have the time, we have the acceleration, we have the final velocity. So that gives us d is vft minus 1/2 at squared. Again, because that final velocity is 0, that term goes away. So the distance to the y at the peak is a negative 1/2 times negative 9.81 meters per second squared times 0.62 seconds squared. Or 1.88 meters. 1.88 meters. And that completes the table. So that last row was a definite step up in terms of the mathematics required. But as you can now see, it can be solved with the techniques that we have available to us. So that concludes the solutions to the angle-launched projectile mathematics physics classroom activity.